Hi everyone again. Thank you all for coming to the second session of the two-parter practical introduction to quantum mechanical molecular mechanic using CP2K for biomolecular modeling. So just in case you need it, the link to the course page is here. I just posted it in the chat to everyone. And I've been asked to remind everyone, I'll remind everyone as well at the end of this session, but I've been asked to remind everyone that at the end of this session, feedback will be open for the course, and we'd really appreciate any and all feedback that we get. This is the first time we're running this course, and we're aware that essentially with the feedback that you give us, we'll be able to make the course better for next time we run it and things like that, and be able to develop the course in the direction that you feel it should go. So with that, one last thing I wanted to say about the link that I posted in the chat. If you follow that link to course materials, you will get to the GitHub page for the course where all of the every exercise problem, every like all of the course material is on that GitLab page. So I've also posted that in the chat. So with that, let's begin the actual course. As before, or as last week, I'd just like to remind everyone that you're more than welcome to reuse this material. All of these, like this lecture as well as the material, will stay available. The lecture will be made available on YouTube. I think I know that last week's lecture is already available on YouTube, and that a link has been sent to all of the course attendees. However, even though this course is publicly available and you're more than welcome to reuse all of the material, please, please make sure to attribute the contents of this course to us and don't profit from, don't go selling the course that we've done, right? Because at the end of the day, it is our intellectual material. Another thing I quickly wanted to mention is a quick how to use Collaborate. I'm aware that Collaborate looks like a lot of these sorts of video softwares, but just in case you're not used to it, I wanted to make sure to point out that Collaborate has an option for raising your hands. If you have a question that you want to, really draw my attention to, please raise your hand and I'll see that. Also, there is a group chat. If you click on the little purple icon at the bottom right of the screen, when it's closed, it should look like two arrows pointing leftwards. And when it's opened, it should have an X on it. You should get this display where if you click on the speech bubble and then click on everyone, you are in the chat for everyone. So this chat here. If you have any questions during the course, please ask them in the everyone chat. The other possibility is if you want to ask a question but you don't want anyone else seeing it, please feel free to contact one of the moderators by going on the little person tab with the number on, and then just send it to Arno, Holly, or Salome, or myself indeed, and we'll get back to you with an answer. So that's how you use Collaborate. And now for today's sessions, what we'll be doing today is, well, to start off, I wanted to make sure that there's no questions from last session. So if you have any questions or anything you want to ask about last session, please write your questions now while I go through this slide. And then otherwise today, we're actually going to start doing some QMMM, because last week, I'm sure you'll have noticed, we predominantly did quantum mechanical systems. There wasn't that much classical happening. So today what we're going to do is we're going to go through an exercise where we are going to look again at our favorite Diels Alder reaction, but now we're going to do it in solution. And for that, there's going to be a number of steps that we'll need to go through, not least of which we will need to prepare our system. We'll need to prepare the parameters for our system. For that, we'll use a program called Amber Tools. We'll also need to set up a QM region within CP2K to tell CP2K this bit is quantum mechanical. The rest of our molecule, or indeed the rest of our system, because it'll have water and other things like that, is going to be simulated classically. And then lastly, I'll talk briefly about some metadynamics that can be used, metadynamic methods that can be used to try to speed up these simulations with greater or lesser effect. After which, there is an entire session of this. So let me rephrase that. After which, there is an entire folder's worth of exercises where you can repeat these processes for a much, much, much larger system that will take much longer to run and is way beyond the scope of this course in the sense of we couldn't run it and get decent results in 2 hours and a half. One thing I forgot to mention in the, or to show on this slide, is at around 2:30 we'll have a break and we'll have a half-hour break, and this time we will have a break at around 2:30 and it will be half an hour. With that said, are there any questions from last week? I'm going to take that as a no. But please do feel free to ask questions. Salome, Arno, and Holly are all here to jump your questions and answer them in chat as soon as you ask them. So please do ask them. We really liked how engaged everyone was last week, and we're hoping to get that again this week. So with that, is that the right slide? That shouldn't be there. Anyways, that is the right slide. Cool. Sorry. With that, let's start going. Let's start going through the exercise by logging onto Archer. I noticed that a lot of you had an account on Archer or had obtained an account on Archer last week. So one moment. There we go. Had obtained accounts on Archer last week. So that makes everything easier. To log into Archer is SSH, your username, which is going to be at login.arch.ac.uk. It asks for a password. And there we are on Archer. I'll get to why getting that error in a sec. BND. Once you're on Archer, as before, you'll need to cd your work directory. Your work directory is /work/TA003/TA003/ whatever your username is. And then once in your work directory, if you want today's, all of the practicals are available here, but specifically the ones for today, you will find in /work/shared, /TA003/shared/practicals to CP2K. And let me just copy that there. Archer link to course. Actually, path of the link. There we go. And then you can just copy it across to your directory. As you can see, I've already done this prior to the session, just to save that 1 second. And very quickly, it's entirely possible. I thought I'd changed them, but I might have forgotten. Reluctance to opt is going to be number 1, subreactants do you opt? Yes. So if you use the newly copied if you use the input scripts that I've told you to get from today onwards, I have changed a couple things in the course material since last week, including some of the material from last week. If you use those, you will notice that the account number, the budget code, has changed. And to answer your question, BND, of why are you getting an error about a submission error on Archer, the reason that you're getting a submission error on Archer is that you are not using the correct budget code. Last week, I'd accidentally put material with the budget code D118. However, people on this course are presumed to be members of the account TA003. Cool. The next question is from Kelly Shankar, which is how do I copy the material? So if you want to copy the material, let's make a new directory. You just cp /work/TA003 shared practical, and you'll need a -r, so cp -r, and then you can just copy to here. Are you getting permission denied for everything, or just for a couple of things? I mean, I'm probably getting permission denied because I'm trying to copy something into something that already exists. Yes, so you won't be able to copy anything from TA03, TA03, TA03JS. That's my personal account. You would need to copy from work/TA03/shared. So from this path. And it seems that a couple of people are saying that it works. So I'm going to assume it works, but if it does not, please put it in the chat and one of Holly, Salome, or Arno will jump on it to talk about it. So once you've copied to cross, you'll notice that there's a couple of directories. There's the sessions 1 and 2 directories on geometry optimization and nudged elastic band methods, which we talked about last week. There's also, I've added a directory with the slides. So if you go in here, all of the course slides are in this directory. Everything is from the GitLab page. So you will always have access to these, even if you don't have access to Archer anymore. But right now, we're going to go into session 3. In session 3, I'm going to go straight into the. I'm going to go straight into the exercise module, but you'll notice that there is with session 3 the markdown page, and if you look at that, this is all of the exercise in a markdown page. So everything I'm going to be doing over this session is going to be talking you through these. One thing I really want to point out as well, while I remember, is that a lot of the things that I'm going to discuss here today have already been discussed in much more depth in a really good tutorial that Salome did. And I think the tutorial apparently it ran in June. And here is the link to that tutorial. Salome went in a lot more details about the Amber tool side of things. Here I'm probably going to brush things a bit more on the Amber tool sides of things to try to get to the running simulations faster. With that, we'll go straight to exercises. What we'll be doing in this session is we are going to take we are going to try to model a Diels Alder reaction in a specific molecule. The molecule that we'll be using is a molecule that you've seen a picture of in the slides. I can show you the picture again real quick. Namely this one. And you'll notice that this molecule has already undergone a Diels Alder reaction, and that the two rings are now connected. We will be starting with the product state for these simulations, and we will start with the product state. We will then add water to the system, and we will then add quantum mechanical, define certain atoms as being quantum mechanical. The reason for starting with the product rather than the reactant is that as soon as you add things like water, especially the amount of water we'll be adding, it's more likely for the two reactants to not come close to one another and to thereby combine. So starting with the product state, and instead of doing the reaction from reactant to product, we are instead going to try to do the reverse reaction and cause the product to break off into the two reactants. I hope that makes sense. And let's go back to, here we go, cool. So the first thing we're going to do is we are going to use first thing we're going to do actually is we're going to be using Amber tools for the first half of this session, pretty much. So first thing we'll do is we will load up the Amber tools module. If you recall from last week, you can see which modules are available by typing module avail, and it will show you a huge list of all of the modules available on Archer. There are a lot of them. The one that we're specifically interested in is Amber tools, which you can find out more about by typing module avail Amber tools. And you'll notice that there's two versions. The default version is the 2015 version here, but we will be using the 2020 version because it's more up to date. To load a module on Archer, you module load Amber tools 20. And now we have Amber tools. We can check this by doing module list, which will list the modules that we have in our setup. So you'll notice the last one is Amber tools. And if we ever want to get rid of Amber tools, we can just unload it with module unload. And now if we module list again, Amber tools has disappeared. Surprise. Cool. So in this directory, and the directory I'm in, sorry, I should make this a bit more clear. I am in the session 3 exercises directory. So the session 3 exercises directory looks like this, and I'm specifically in the first part of the exercise, the system setup. And during this exercise, we're going to do a number of things. We'll start off by setting up our system parameters using Antechamber. We will check that our system parameters are sensible using a tool called ARCHER2. And then finally, we'll hydrate our system using a tool called LEAP. All of these tools are available as part of the tool suite. And you can read up about them on the Amber Tools website. I believe the link is in the exercise file, 2 directories up from there. So with Antechamber, we want to generate a topology. And the way we do this is by running the following command, Antechamber, very quickly, just to show that it is an Amber Tools or part of Amber Tools. When I autocomplete, it autocompletes to Antechamber. However, if I unload Amber Tools and then try to autocomplete Antechamber, it doesn't find anything. why we need, it's one of the things that we need tools for. So antechamber, and what we're going to do in antechamber is when we're going to input our product. So the flag is -I for defining the input, and our input is product.pdb. We're then going to say our product file, what type of file it is. So -fi, the type of file that the input is a PDB file, because it's called product.pdb. Next, we're going to output it as a Molden file. Molden is a type of Molden is just a way of writing your particle parameters, so your positions and your positions, your bonds, those things. But it's one CP2K is more happy with than a PDB input. CP2K is not too keen on PDB. So we want a Molden file, so our output file is going to be Molden. And then we're going to need to tell antechamber what the net charge of a system is. Now, the net charge of our product system is actually -1, -1. There's one more electrons than you'd expect if it was entirely neutral. So we need to tell that to antechamber for it to generate the correct, the appropriate for it. How do you determine the net charge? That's a great question. Second question that I got was from Kali Shankar, which is, please could you explain minus net charge, NC -1. NC is net charge. So we're saying at the moment, we're telling our system that it has a net charge of -1. N for net, C for charge. BND asks, how do you determine the net charge? That's a really good question. So there's a number of ways of determining net charge. A number of tools that can be used specifically for this one. I don't remember how we determined it for this, but if I recall correctly, essentially there's a number of programs that you can use to find the net charge of your system, and I'm just trying to remember which one will be used for this. Do Salome or Holly remember which program we used for this specifically? Perhaps. But if I recall. But to find your net charge, you can also just so yeah, to find the net charge of your thing, you can use certain software like H++. I'll put a link in the chat. H++, or also you can use Proeme. And these are software that you can input your molecule into, and it'll tell you, okay, with what you've put in, you're going to have a net charge of this. So that's how we found the net charge for this one. Does that answer the question? Cool. So where were we? Oh, cool. Thanks. Where were we? So we've defined the net charge of our system, and then finally we need to add a couple of definitions. So one of those is we want to tell, we want to say what sort of essentially what sort of crystalline structure we want to pretend our system to have. In this case, it doesn't matter too much, so let's just go for body-centered cubic. And then we want to say what parameters we want to use. And the way we do that is with -AT, and we're going to use the GAF2 force field in this case. So we're essentially saying, take the position of the product, make a new position file but in this case, also add that the force fields should be assumed to be GAF2, and that the system has a net charge of -1. And then finally, we're gonna do Rn, which is the residue name, and the residue name is going to be DAA for Diels Alder. Then we just run this, and this is going to take about a minute to run, and it's a fair amount of information. So it's going to look for geometries, open the PDB file. Warning: there's more than 10 residues. It's going to output warnings when things are a bit strange. La 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 la, and then we get to the end. It says that the total number of electrons is 236, meaning that the net charge is -1, which it's doing because that's what we've told it to do. You could easily, if you wanted, you could easily tell antechamber that your net charge is +1, and then antechamber would find a way of making sure that your net charge was +1. Your system might not be physical when you do that, but hey, I mean, if that's what you want to do, that's what you want to do. So as I said, this takes about a minute to run, but not much more than a minute. Could I display that command again? Yes, that's a great idea. Thank you for the suggestion. I'll put it in chat. It'll be easier for everyone. But the command looks like this. No worries. And the other thing very quickly I wanted to point out is all of the commands that I'll be talking about today are from exactly this page. I mean, to be quite honest with you guys, I've got this page open in the background to make sure that I don't make any mistakes. But yeah, all of the commands that I'll be running are from this page. If you ever get lost, if you're ever worried or anything, you can just copy paste from that page. It should work. If it doesn't, let me know. I'll fix that page. Huzzah, it's run. So once it's run, you notice there are a ton of new files. Sorry, Salome brings up a quick comment on net charges before we go on to that. We have to be careful because with the net charge of our systems. We can use the links that I've used if we have organics molecules, but you might also want to try the biochemical database. So yeah, there's a couple of extra links for that. Thanks, Salome. Is it the same process when you have a protein? Yes, it is. And indeed, the exercise that I'm leaving up to you guys is you're essentially doing exactly the same steps as we're going to do today, but you'll be doing it on a protein rather than on a small ligand. Yeah, cool. So there's a bunch of new files, and most importantly of all, there is our product.mol2 file, which is the output that we were looking for. I seem to recall, I might be wrong, but I'm... Oh, cool, I was wrong. Product.mol2 is our Molden file, and as you can see, it's got... Here we go. So it's got everything that we want. So it says, you know, the BCC that we've defined. It's got all of our positions, all of the names of our particles, all of our bonds, etc., etc., etc. It's now a mol2 file. So the next thing we're going to do is we are going to use parm checker. We're going to use parm checker to check that our force field is sensible. Parm checker is another. I can type. Parm checker is another of the Amber Tools suite, and in this case, we're going to parm check our new product, product.mol2. The type of file it is -f is a mol2 file, and we want the information from this. So we want the parameters generated, the force fields generated, to go to a file called system.prmtop for now. .prmtop is just a type of file that can hold force field information and things like that. Whoops, sorry, did not mean to do that. Did not mean to do that either. There we go. 1 second, let's clear that to make it a bit more clear. So parm check like that. And then that runs in seconds. I'm going to again copy the command for you in chat. There we go. Yep, so we run parm check. And then finally, we are going to do, very quickly. So ls minus lrt is a great way of sorting things in the time at which they were output. So you'll notice that the top file has the oldest time, the bottom file has the newest time. And there you can see that the very last thing that's been output is system.prm top, which is what we wanted. And this one, I'm pretty sure, has information about the angles of our systems, the improper angles, the dihedral angles. In this case, we don't have any dihedral angles, and things like that, and gives just straight up, it gives the energy parameters for the angles and things like that. So at the moment, we are still, by the way, just want to emphasize, we are still doing a purely classical approach to this. There's been no QM yet. We are preparing for QM, but there's been no QM yet. So the final thing we want to do is we want to use Leap. And Leap is, again, part of the Amber Tools suite. And we're going to use Leap to do two things. The first thing we're going to do is we are going to use Leap to solvate the box. So you'll notice that this line here says solvate solvate ligand, whatever lig is, or lig, whatever lig is. You'll notice that lig here is just our molecule loaded, or the product loaded. And we're going to add tip3p water in a box in our ligand. The next thing we're going to do is we are going to add an ion. Because our system had a net negative charge, so it had a negative charge of -1, we are going to add a single positive ion, sodium, to offset that net negative charge. The rest of the things that are in this file, the source here is, we're telling Leap, please use specifically the force field parameters from these 3 force fields. Also load the parameters that we've already checked using parm check. And then we want things to be saved as system.pdb, and we want things to be saved. We want to save our new parameters in system.inpcrd. You could name it product dot, should system.prm top obtained in the parm check to be named product.frc mod. Yeah, so it's possible that we've, or that we're not going to be using that file after this. So because of that, you could name it that if you wanted a backup of it or whatever, but it'll still be overwritten, so that should be okay. Can the previous commands be added to leap.in? I don't think so, but I might be wrong on that. I am not the expert on Leap or on Amber Tools, unfortunately. So we've got our input, and we are now going to run dleap -f leap.in. -f means, so tleap is the name of the command, T for terminal. Normal leap is a visual software, and running anything visual on Archer can take a while to load up. -f, we are saying we're going to read the input file, leap.in. Press enter. It tells us an error. That's probably because I've made a mistake. Leap.log. Where is the error? That might be why, yeah. And it did indeed exactly what you were saying, Jordi. You called it. Well done. So in parm check, that should have been FRC mod. Sorry about that. I can't even copy paste from my own page. The command for parm check looks like this. Have I run that? I have run this. And then tleap minus fn. And maybe even call it product.frc mod. Yay, it runs. So apologies for that, everyone, and very spotted Jordi, by the way. The command should be the last one I've put in. And there, once it runs, you'll notice that tleap runs perfectly happily, and then outputs everything into the log file, as well as, so yeah, there's a log file, as well as the 3 system dot files that we've asked for. So system.prmtop, system.pdb, and system.inpcrd are the last 3 to have been written. One quick thing I want to point out about the leap.log file, this is something that I find a bit irritating, but that's probably more just me than anything. If you go through the system.log file, you will notice that it keeps every run that you've done. So unless you get rid of the log file, you will have all of the logs of every run that you've done in the specific directory, including the ones with, what was it? It was fatal error, I think. There we go. So even the fatal error stuff is still in there, even though this was 2 tests ago. There should be another one, by the way. There we go. Yeah, there's the second one. Cool. So at this point, what have we done so far? Well, we've managed to take our PDB and make it into a format that will eventually be more useful for for running in CP2K. We've also created our system parameters, and we've created a system input. So system input and system parameters. And now with that, we've got the starts of our system that is fully solvated, which we've just solvated in tleap, that also has a net charge of 0, which is useful for if you don't want your system to blow up. And we can now proceed to the next step. The next step is we will be using a, sorry, I'm going to check, are there any questions? That's a good thing to point out. Parameter file was not saved. Interesting. So possibly the reason for that, Kali Shankar, is I'm not going to get too bogged down on this, but I think possibly part of the reason for that might be that tleap tends to not want to overwrite files. So it might be refusing to run that because of my previous mistake. There might already be a file called system.what was it? PRMod. So if you get rid of the system.prmtop, as in just rm system.prmtop, and run it again, it should hopefully run. However, even if it did not run, I did envisage that maybe there was going to be some issues with the running. So I have made a directory. Let me go back up. So in the exercise directory, for every single exercise, we're going to need parts of the previous exercise's input or outputs. And to make sure that this wasn't an issue, I've made sure to have a backup of a system.inpcrd and system.prmtop that both work for that system. Meaning that if you want to keep following on, you're welcome to follow on because you will still have the necessary inputs. And indeed, hopefully, backup system.prmtop should look exactly the same as prmtop. There's one small I can't spot the difference there. Right. So now that we've finished our setting up our system, we're going to do a quick classical equilibration on our system. And for this, we're going to need both the system.prm top file that we've just generated and the system.input crd. As I said, if you've not been able to run these, these can be found in the backup misstep folder. So now what we're going to do is we are going to use another part of Amber Tools called Sander. For this, Sander can take a while to run, so instead of running it on the Archer login node, we will instead submit it to the Archer queues. So we're going to be running two, let's look at the submission script first. We are going to be running two Sander jobs. The first Sander job is going to be running Sander. We are going to do an energy minimization. And we're going to input this file. We're going to output this file. And then we're also going to use the parameters from here, the configuration from here, and we are going to output some of the data into system min.r. Then we will use, so I think -r is the final output step should go to this. Then we are going to use Sander to run a thermal equilibration. And in this case, we are going to take as, again, our input parameters are still the same as before, but our starting configuration is now the final configuration from the minimization step. So essentially, we're going to do energy minimization and then thermal minimization, or rather, we'll wait until thermal equilibrium is reached. This time we'll output to there. And we'll also output, I can't quite remember what the MD&C file is, but I don't think we used it afterwards. I'll have it after it runs. So let's have a look at classical minimization. And here we are just telling Sander what we want to do. What do we want to do? Well, we want to run things where the cutoff distance is a distance of 8 angstroms. We want to run for a maximum cycles of 4,500. Minimum cycle is 1. And other information like so. And after that, so this is just to say what sort of energy minimization we want to do. After which, we will run a heating minimization, and for that there's a bit more data. So what do we want to do? Well, here to run the heating part of the thing, we need to define things like our time step. We're going to have a time step of 2 femtoseconds. We are going to define our temperature. Of course, it's important you can't reach thermal equilibrium unless you define your temperature. Our initial temperature is going to be 0. We assume that our system has not been relaxed at all. Our final temperature is going to be 300 Kelvin. We want to run for 10,000 steps. Our cutoff is the same as before, and a few more commands. If you want more information about Sander, I believe I gave a link to Sander. I think yes. So in the course tutorial, I gave, instead of a link to Sander, I gave a link to this Amber Tools tutorial, which teaches you about the use of Sander and a lot more of these, what's the word I'm looking for, of these parameters that you can play around with. So once we've got our input files, the system input and the system parameters, and we've got our two submission script, our two Sander files, we can just qsub, sub Sander, and it should run. And then we can see how fast it's running with qstat minus u user. If we watch this, it'll just show us how quickly it's running. And yeah, it shouldn't take, because we're running on the short queue and all of the work that's being done for this session is going to be run on the short queue, you'll see that it should actually just queue quite quickly and start running quite quickly. If I recall correctly, the Sander jobs, both the Sander equilibration and the Sander thermal equilibration should take under a minute to run for this case. So at this point, are there any questions about stuff so far while we're waiting for stuff to run? Error in opening unit 8 file system.prmtop is missing or unreadable. Kelly Shankar, is that in answer to what Salome was asking you, or is that a question directly to me? Do you need to move those files into the new working directory? Yes, you do. So I've made it so that you can just swap directories to be in directory 2_minimization. But you will need in that working directory, the way things have been written, you will need to have system.prmtop and system.inputs inside this directory. Of course, you could, if you wanted to, you could, I imagine, I've not actually tried this, but I imagine that you could direct your -p to some other directory, I imagine. So you should probably be able to do something like *, wildcard system prmtop, and it should still work, would be my guess. I've not tried it, so I can't confirm whether that's absolutely true. But that would be my guess for that. How do you ensure minimization and equilibration were fine? So this is something that in the Amber tool specific tutorial that I linked to earlier, Salome went into great details about that. But basically, there's a number of output files that are generated. Let's have a look at the output files generated. Let's actually exit. There's a number of output files that are generated, including in MD info, and MD info outputs for every time step, if I remember correctly. Nope, not for every time step. Which one is it then? I think it's system. Sorry, just quickly going to look through files. Yeah. But yes, so basically, MD. Yeah, so basically at the moment we've just done a very minimal MD info, which was overwritten during the thermalization, so it only shows the final step. But you can set how often you want to output to MD info, and you get information like the total energy of the system, the kinetic energy of the system, the potential energy of the system, things like that. And from those, you can check whether your system has stabilized, especially if you've used more outputs. You can check whether your system has equilibrated by essentially seeing whether your temperature has stabilized and is at around 300 with very little fluctuations. You can check your energy is equilibrated by whether it's reached a plateau and is not wildly fluctuating, that sort of things. In this case, in the interest of saving space, we've only output the final thing, but we have checked previously that this is sort of the rough, for the system sizes that you're looking at, we've run this for 10 picoseconds, and 10 picoseconds. Oh yeah, there we go. Thanks, Salome. Yeah, cool. Thanks, Salome. So yeah, I saved those as out.classical minimization. Yeah, so this is the log file for the entire run, and you get all of the things like the energy at each step, and you can check that your energy at each step is not fluctuating too much. So as you can see, it's sort of like not moving too much at the point for the energy minimization, and likewise for the out.heating. You'll probably be interested in things like, well, when the energy, is it changing? The energy will fluctuate a bit more here. But yeah, you can look at the energy, whether it's changing. You can look at the temperature as well to check that it's roughly at the right level. At the moment, we're way too early in the run for it to be at a sensible temperature, but you can look at the later temperatures and check that things are looking about right. And as you can see, that the temperature is sort of like here at roughly sensible values. The energy is not fluctuating too much between these steps. So that's how you can kind of look. This is a very quick by the eye thing, but of course you could write a simple bash script or Python script or whatever your favorite programming language is in order to make this chunk of data look a bit nicer and a bit more plottable. I hope that makes sense. Oh, and apparently Salome points out that you can also use Sander with, you can run Sander with a -O flag to put your output out, and it'll sort of give you better results. I'm not going to try doing that live, but again, all of this is in the previous Amber Tools tutorial that Salome gave, and as you can see, clearly Salome knows her stuff on Sander and on Amber Tools generally. At this point, again, I just want to quickly emphasize, like we're probably going to take a break now, or we are going to take a break now. But before we take a break, I wanted to quickly emphasize that for the next step, which is going to be running a QMMM simulation, you'll need some inputs from the second step. However, even if you've not managed to run the second step, don't worry, because again, I've got parameters that will work from the second step, so it feel like you're running behind if anything, if you've not had a chance to run these simulations or if anything's gone wrong. With that being said, I make it 2:30, which means that it is time for our promised half-hour break. I think maybe we'll make it, shall we aim to get back at in 25 minutes at 5:02 instead of on the hour? And if anyone has any questions about anything, if anyone wants to, like I noticed that some people have struggled to run certain things, I'm going to stay here and answer questions on chat if anyone's got any questions. So with that, I guess I will see you all in 30 minutes. Let me get the slides back up real quick. Right. So we have done a large amount of the work necessary to prepare our system in a classical fashion before running it in CP2K. Now we're going to do a last couple of tweaks to our force fields. One of the tweaks will be we want to ensure that the water parameters are the tip3p parameters that we want and are correct for the way CP2K interprets force fields. And the other quick thing we want to do is we want to make sure that the what's the word I'm looking for? That the force fields, the classical force fields, are also rewritten in a format that CP2K is happy to use. So with that, let's go back into Shell. Cool. So we're back in Shell. I'm not going to spend any time sort of looking through how to get back on Archer. I imagine that by now you're able to, or you've not gone off of Archer, hopefully. So for this, we are going to go into the third session exercise. And again, like time, for those of you who, for whatever reasons, were not able to run through the steps, everything that we'll need for this exercise is in the backup missed steps. And hopefully, you'll see that if everything's gone right, this should be, they differ. Oh, well, cool. In which case, I will definitely be using the backed up ones because I've made a couple, as you saw, I made a couple of mistakes with the parm checker in the first session. So the way you do that, if you want to use the inputs that I've already put in, the ones that I have tested and should be correct, fingers crossed, you just CP backup missteps system.md.r to the current directory, and then system.parmtop to the current directory. And now if you ls-lrt, you'll notice that both of those files have been copied over. So for this, we are going to be doing 3 different steps. The first step we're going to do is we are going to use Amber tools. Specifically for this one, we're going to use Parmed, which is my favorite Amber tools piece of software. We'll get to why in a sec. We're going to use Parmed to run this input.parmed underscore tip3p, to make sure that our waters have the appropriate Leonard-Jones parameters, especially the hydrogens, have the appropriate Leonard-Jones parameters for tip3p water. The way we're going to do that is we are going to use parmed parmed system.prmtop minus I for, we want this input file, and the input file is input.parmed tip3p. Press enter, and this will launch parmed, open system.prmtop in parmed, and run all of the instructions within input.parmed tip3p. You could easily just have launched parmed instead and loaded system prmtop within parmed and then run all of the commands within the input file instead, but this is just faster in my opinion, and works quite well. And here you have it. This is probably why I find parmed to be the most amazing tool in Amber tools. Check out that lovely ASCII art. And the most exciting thing, in my opinion, is that if you run it again, I think they've got like 8 or 9 different pictures you can get, like a Game Boy. Yay. I find that superb. One of the questions, if I was using a charmed force field, would these Leonard-Jones parameters still be modified? I'm not sure, is my honest answer for that. I think what I'm saying might be wrong, and someone will. There we go. Yeah. Salome says that if you want to use tip3p instead, then yes, you will need to still modify the parameters. The other question is, what if some waters do not have the correct parameters? I'm not sure exactly what the question you're asking is. At least if we follow the recipe that we've taken up to now, all of the waters should have the correct parameters. So unless you've gone in and changed them, then they should have the correct parameters. Okay, cool. So if you're getting command not found parmed, that may be because you don't have Amber tools loaded. Could you try running module list and checking that Amber tools comes up as one of them? And if not, module load Amber tools 20, and I'll copy that into the chat in case. Cool. If that's still an issue with tool, please post again in the chat and someone will help you in the chat. Right, so we've run Parmed, which is the most amazing bit of software because of the ASCII art. What next? So the next bit, as I mentioned, CP2K looks for particular parameter files, and CP2K looks for specific parameter files, and we need to make sure that those files are in the format that we want CP2K to read. So for this, what we'll need to do is we'll need to take the system.md.r, which is the final output position of the heating equilibration that we did prior to the break. And we want to make it into a format that CP2K will be happy to read. In this case, we want a CP format. The parameters, the thing, this shouldn't change the parameters. This will just change the input file to make it legible for CP2K. So how do we do that? Much like with Parmed, what is auto image? That's a very good question. I believe that in the actual course notes, I have put a link to the CP tool, CPP trajectory tool website. So there's the notes to that, and auto image is a way of automatically centering an image by the molecules and having the periodic boundary conditions. Yay, I said the same thing as Salome. I'm learning. So, where were we? We got our input for CP trash. So now we just need to run it through CPP trash, and in very similar CPP trajectory. And in a very similar fashion to before, we're running CPP trajectory system.purm top minus I dot CPP trajectory reformat. It happily run. This should not have been. I'm surprised it's taking so long, actually. Just wanted to scare me. And then we're left with the new file that we've created, system.leonardjones modified is the file with the new 3p parameters that we've been in Parmed, and md.crd, system.md.crd is the positions that have been made so that they're readable with CP2K. So we are finally at the stage where we start considering, it's only taken 1 day's worth of course of looking at QM, half a day's worth of course at briefly glancing at molecular mechanics methods. We're finally about to run a QMMM simulation. And how this is going to work is as follows. Let me quickly share the slides. This is going to work as follows. Basically, we are going to, if you imagine, our molecule looks like this, looks like the thing on slide. And what we're going to do is we are going to cut it so that only the bits around the ring, so only the bit where the atoms have an index, are going to run in a quantum mechanical fashion. Because that's the bit that does the reaction, right? That's the bit that we want to see unbind. We might not get to see it unbind. We'll get to that in a sec. But yeah, that's the part that we're interested in terms of where the reaction or the interesting things happen. So that's where we want to spend our computational power, because QM is very, very much more expensive than molecular dynamics, or at least classical molecular dynamics. So we want to restrict it as much as possible. So we're going to take those atoms that are numbered, and we will run those in a quantum mechanical fashion. And at atom number 5 is going to be our switch from quantum mechanical to molecular mechanical. And everything that is not one of these numbered atoms is going to run classically, and everything that is one of those numbered atoms is going to run quantum mechanically. And now I'll show you a bit how you can set that up in CP2K. So maybe I should actually write the right input. There we go. Here's the CP2K input that we'll be using for the simulation. And actually thinking about it, to save a bit of time, what I'll do is, I'm aware that this takes about 10 minutes to run. So I'm going to submit the simulation. I'll show you what's in the subscript. The submission script is exactly like the ones that you saw last week. We're going to be launching this on a single node. The system is so small that running it on more than a single node actually ends up, you lose time in communication rather than gain time in compute power. It's going to take a maximum of 20 minutes. I've actually timed it should take about 10 minutes, which is why I'm going to launch it now and then go through the input script. I'm going to try to submit it to this special queue. Everyone has access to it. It's the short queue for if you want to run jobs that are less than 20 minutes on less than 8 nodes on Archer, you can submit to this short queue. And the job is going to load CP2K, like last week, and then is going to run parallel CP2K with the inputs we're about to look at, and then it'll output that file. We'll look at that in a bit when it's done as well. So I'm going to submit this now. Hopefully there's not too many people using the short queue. But yeah, I'm going to submit this now, and hopefully it'll run while I'm talking about the input. So our input is very, very similar to the input we had last time. There's a couple of key differences, though. So I've named the project QMMM instead of, I think, reactant or transition state or product is what I named the ones for the geometry optimization parts of the exercise last session, or nudge elastic band or something like that for the nudge elastic band. I set my print level as slow. Run type, MD. I'm specifying that I want to run something which involves molecular dynamics somewhere. In my force evaluations, I defined that my method's QMMM. So now already, CP2K will reach this and trigger to the fact that this is going to have quantum mechanical and molecular dynamics. The DFT section is very similar to the ones last week. So method is PM3 again. There's a quick step in the quick step section. Charge is 0 because that makes everything easier. There's an SCF section, much like last time. And then at the end of the DFT method, we have something new. We have the MM method, the MM section. And in the MM section, we need to start defining things like force field. We tell CP2K that the force fields we're using are amber force fields. We tell CP2K that the parameter files that we're using are in the in this file, and you'll note that this file is the file name, or this file name is the file name for the where we've added the hydrogen parameters. So I've got a question. The question is there any software where we could pick the atom that will be part of the QM region and then save them as part of the CP2K input file? So I can possibly answer that a bit later. I intend to use a bit of VMD, and with VMD, you should be able to click on atoms to see what their atom IDs are. And yeah, sure, you will need to write them down and then copy them into CP2K. I'm not aware of a software where you can visualize, click on the atom specifically, and then it'll produce your CP2K input file. But there are many software MD being one of them, where you can click on specific atoms, get their IDs, write down their IDs, and then use those when setting up the QM region. I hope that answers your question, Andre. So carrying on with the input file. Yeah, cool, brilliant. So the input file has, yeah, so it's the same input file with the modified Lennard-Jones parameters. We then need to define a couple of things about our molecular mechanics simulation. And you'll note this specifically for the classical part. We define things like so yeah, we define the force field, we define the cutoffs for the force field. Sorry, the cutoffs are there for 10 angstroms. We define, I'm not quite sure what Emax plane is, but I'm sure I could look that up. And then we define the Poisson part, which is just say how we want the system to be able to move. We define then a couple of subsystems, and we'll need a couple of subsystems, you'll note. The first subsystem with a cell, and so this cell just defines what the simulation cell looks like. The topology defines, you know how last week we were entering the coordinates one by one. If you want, you can instead use the topology section to say, well, I just want to take in this file and input that, and I want to take in this file and input that. And in this case, the two files that we're taking in are the connection file format, so telling us what all the connections are, what all of the parameters are, what all the connections are, and we want the coordinate file, i.e. what the position of all of our particles are. I heard that there's a question. I'm going to quickly have a look at that. It starts with, please finish the walkthrough first, so I will finish the walkthrough. Then, this right here, well, this entire section right here, actually, you remember how in the very first part of this exercise, one of the things that we did was we subated our ligand, and we also added an ion to make the charge neutral. When adding that ion, to make it easier for us to read, to make it easier for us to understand, the ion we added, I believe we called Na+, uppercase. Na+ is not an element that CP2K is aware of, not written in uppercase N, uppercase A+. So here what we're doing is we're telling CP2K, if you run into something called Na+, be aware that's just a sodium. And here likewise, we're saying if you run into something that's called uppercase C, uppercase L-, be aware that's just a chlorine or a chloride. And there we've set up, in this subsystem, we set up our entire classical system. And the quantum mechanical will be part of that class, or will be within that classical system. But we decide, we begin to define it next in the QMMN part. And in the QMMN part, we define, so again, we define the cell of our QMMN region. We define the type of coupling that we want, Coulombic coupling, and then we start defining one by one the different atom types that we have. So we have one nitrogen, and it's atom number 33. If you remember, and I'll put back the picture that I showed earlier. So if we look at atom 33, where's atom 33? I'm going to guess atom 33 right there is that blue one. Yep, that looks like a hydrogen to me. Does that look right? 3, 4, 3, 5. Yeah, that looks about right as well. Cool. And notice, I don't know, for instance, that 16 and 17 look like they'd be oxygens. Hopefully, if the picture matches the input file. Hello. Oxygen, there we go. 16 and 17 are defined as oxygens, or as are indeed atoms 30, 35, and 37, which are also oxygens in the picture. I'm going to put a link to the slides. for anyone who wants to follow the slides as we go and check that the pictures do match the things that we're saying in the input file, we define things like carbons, hydrogens, etc., and we're telling CP2K this is a hydrogen, this number, this number, this number, this number. Guess what? They're chlorines, and I want you to treat them in a QM fashion. And then we say the linking atom. We tell CP2K the final QM atom is atom number 38, which was the hydrogen, 38, which was one of the carbons there. And then we tell CP2K the first MM atom is atom number 5. And then we tell it that we want to use the IMOOM method for linking, and the IMOOM scheme is a scheme that adds an additional atomic center, so a fake hydrogen that's, in a fake sort of way, bound to the final QM atom, which has no real value, and its purpose is only to make sure that there's no free bonds, if that makes sense. And that fake hydrogen atom is going to be placed in the center of the first MM atom to make sure that everything is bound nicely and that everything has all of the bonds that it would need. Cool. Arno seems to have answered the question from BND. So yeah, so that's the force evaluation method, force evaluation part. And if we look next at the motions part, well, you'll notice that the motion has, if you like me, you come from a classical simulation background, it has a lot of things that you're sort of like used to. So it's got things like you set your time step and it's set at a 0.5 femtoseconds. Number of steps, you've set your temperature, you set your barostat thermostat. That's all stuff that, you've ways to keep your temperature, your pressure the same, because we are running an MD simulation, or an MD-like simulation. Actually, I'm not happy with that. Sorry. Where was I? Yeah. Yeah. So we define our barostat, we define our thermostat, and then we say, okay, we want to print a restart every 2,500 time steps. Our trajectory that we want to output is in a DCD format. We want a trajectory to be output every 100 time steps. Actually, this is probably every 4 time steps rather than every 100, because I wanted a lot of outputs to check that something interesting was happening. But you can always play, you can play with things to make your simulation more interesting or longer. You can play with things like the number of steps. That's how long your simulation is going to be. The time step, that's how short or long your time step is going to be. You probably don't want to go much higher than a time step. Though for MD, you probably don't want to go much higher than a time step of maybe 0.5 to 1 femtosecond, but you can definitely go up that far. You can set things like, how often a restart file is written, how much you want to keep track of your restart history, and things like that. And then once this is done, oh yes, I've indented it a bit better. Once this is done, you can submit your job, and hopefully it's running. Hey, it's run. Cool. I heard that there was a question, so I'll look at the question and then I'll look at the job. Can you have your QM time step be smaller than the MM time step? Maybe have it as a multiple of the MM time step, so the QM time step. Center is the center of the QM region. That's not the answer. I think Holly is probably best at answering that. I'm not sure about that. I know that there are ways of doing that when you link CP2K with other things and have CP2K running just the QM part. and whatever the other MM software or MD software runs as just the MM part. You're able to then have different time steps. But I don't know whether that's doable within QMMM. That's a very good question. If it's not answered within the session. Arno says that CP2K does support multiple time step for MD, but he's not sure whether that's for QM or and MM as well. Cool. So the job has run. That's always a good sign. I seem to have outputs. That's also a good sign. I will start off by looking at output.out, and the job has ended. Usually the telltale sign for QMMM of has it ended properly is that you get the program ended at. So one of the easiest ways you can tell whether your CP2K program has run well is you just tail, and if you get something that looks like that, then your program's ended properly. If it hasn't ended properly, you usually get another bit of fun ASCII art, which is a man holding up an abort sign, or a person holding up an abort sign. I don't think it specifies. But yes, so let's go back to the top. You can see that the simulations run, and much like before, even though this is a low output file, meaning that we're only outputting what CP2K deems the most interesting parts of the simulation, there's still an awful lot of text and an awful lot of stuff. So you can see, for instance, at some point it's running the so this bit, whenever you see the convergence, this sort of convergence graph, that means that it's running the QM part of the code, and then it'll work out, it'll tell you, okay, well, what are my different energies? Remember that, it happily tells you all of those energies are in electron volts. So you'll see the core repulsion looks like this, the core Hamiltonian looks like this, 2-electron integral energy looks like this, etc., etc. Usually the one that I'm mainly interested in is the total energy, but if anything goes wrong, I tend to look at these to see where something might have gone wrong, like if my system crashes, why has it crashed? I'll look at those. And then for every time step, it'll sort of give you that information and then run a new convergence. And then it'll give you that information and then run a convergence, etc., 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 going forward. And then, as you can see, go CP2K go, and it tells you a bunch of information. Cool. Where was I? So as you can see, it just happily keeps running. I want to check a couple of things first. Sorry, this is probably terrible to look at. There we go. What was I looking for? Yeah, there we go. So, so you get all of this information for the QM part of the things, and then you get the MM information following it. And you can tell that it's the MM information for a couple of things. First of all, you've got, ensemble type, NPT, so you're running in isothermal isobaric, you're keeping the pressure and the temperature the same. And then it tells you step number. So that tells you step number, that tells you you've gone one step further since last time. It tells you how much time your simulation's gone through, the CPU time per second, how long this step took, how long it's been taking on average per step. Energy drift is how much of a difference in energy your atoms have been feeling, your pressure, your energies. Yeah, there you see the total kinetic energy of your system. You see the total potential energy of your system. You will notice that, unfortunately, again, as I've mentioned, I come from a very classical molecular dynamics background, I am not the biggest fan of the heart tree as a unit, but CP2K developers are, so most of the energies are in heart tree. I believe one heart tree is I can never remember the conversion, but I think it's something like 600 to 1, but I can't tell you in which direction. Give me a sec, I wrote it down in one of the course slides. Yes, one heart tree or one arbitrary unit is 627.5 kilocalories per mole, or kilocalories per mole. So bear that in mind if you think, small changes in heart trees can actually hide large changes in, or what appears to be small changes in heart trees can hide huge changes in kcal per mole. So do bear that in mind when you look at these things. You've got your pressure, your thermostat, barostat, etc. And yeah, that's output every so often. So at this point, I'd like to mention a couple of things. The first thing is one of the properties of interest is probably going to be is there a total energy, potential energy, total kinetic energy, QM kinetic energy? Yeah, so I can't find a total energy, to be honest. Yeah. But where was I? Sorry. Cool. Right. Cool. So you should be able to just output the information, the information that we were just looking at for every time step by running something like this. Hopefully, that looks terrible. Yeah, I didn't get that right, did I? What did I do? 16 and step. Still not the most happy, is it? Oh no, I'm being an idiot here, aren't I? Sorry. Yeah, so you should be able to output using grep the bits of information that you're interested in. I can't find total energy just straight off the conserved quantity. That could be it. Nope. Maybe if I put conserved rather than conserve. There we go. So you can see how this varies with time steps, and you can even, and 1, 2, 3, 4, 5, and then you can even run GNU plot. Did I say 4 or 5? 5. Hopefully that runs. Is that the value I'm looking for? Possibly. I don't know. Sorry. Yeah, so you can like plot in GNU plot. Admittedly, you cannot see my GNU plot. Give me a sec while I. There we go. Hello. And yeah. So this is a plot of time step versus the conserved conserved quantity in the y-axis, time step in the x-axis. There we go, now with labels, looks a bit better. And yeah, you can see not much is happening. And there's a reason for that. There's a very obvious reason for this, which is I said at the start of the session that we're aiming to run this simulation to try to get this system to go from its product state, i.e. from post-reaction. We want this system to sort of like break apart into its reactant state. Naturally, this happens. I mean, all reactions are, like even at thermodynamic equilibrium, you'll have some forward and backwards reactions that take place. So naturally this happens, but the timescales in which this happens can be incredibly large. And in this case, the timescales are definitely, the only thing that we can say for sure from this simulation is that the timescales in which this happens are larger than the 1 picosecond that we've simulated. Our time step was half a femtosecond. We've run for 2000. That makes it, we've run this for 1 picosecond. 1 picosecond is nothing in reaction dynamics time. So it's not surprising that we're not seeing anything here. Part of the reason that we're running for such a short time is because, as I said before, I've timed these and this runs in 10 minutes. How long should it be? So that's a very good question, B&D. For CP2K like this, I don't know. For simple CP2K, I am not quite sure what the reaction time is. I ran a couple of simulations for 4 hours earlier today. They were still nowhere near having the effect of interest. But then again, I'm not sure that, like, given which reaction this is, I'm not sure that this sort of reaction is simulatable with pure CP2K as is. And that's why we're going to go straight into the next section where we're going to talk about metadynamics. Go back to the terminal. Boom. And for metadynamics, if you go into part 4, I'm going to again submit. For metadynamics, it's this script is quite similar to the previous one. I don't think that diff will do it justice. I'll try diff, but I'm not sure it'll do it justice because there's going to be a number of changes, and yeah, that's what it looks like. Cool. So this script is incredibly similar to the last one. You'll notice the project name has changed, but it's still print level low, MD. The QM part here looks the same. The DFT part looks the same. The SPF part looks the same. One of the questions, do you know any papers about recommended times depending on the type of simulation? I think that very much depends on the reaction that you're looking to simulate. I think basically, I think that is very much dependent on which type of reaction you're looking at. I imagine there will be literature out there already. I'd recommend something like Web of Knowledge or something like that to, like one of the paper journal aggregators, and look through that to see if someone has done a simulation which is similar to what you're trying to do. Even if the similarity is it's just the same bond breaking or forming. I hope that answers that. But yes, back to the input file. The input file is very much similar to the last one. But there's a couple of changes. The first change is here. You'll notice, wait, no, I'm telling, that is not where the first change is. My apologies. So yeah, still linking type is IOMM. The change will be here. There we go. There, first change is here. We've got a new section called free energy. And in that free energy section, we are telling CP2K we want to do some metadynamics. And for that metadynamics, we want to use Plume. I'll get more on that in a second. We want we want to use plumed, and specifically we want to use this plumed file, this plumed input file. I'll show you what that looks like in a sec. Following that, we get to print stage, which is very similar to the one before. Print history is very much similar to the one before, and then that's it. So the real change, the real only change to this input script versus the last one is we are now telling CP2K we want metadynamics with plumed. So what do I mean by metadynamics and what do I mean by with plumed? Let's go back real quick to the slides. So by metadynamics, what I mean is, so imagine that we're, as I said, we're in the product state, meaning that we're in some energy well somewhere. Imagine that we're stuck in this energy well, but we want to have a look at the rest of our energy landscape of what's around where our simulation is running. How can we do that? Well, one of the ways we can do that is to use a form of metadynamics where we choose some form of collective variables, a set of variables, or even just one variable, but a set of variables that we will track in order to force our simulation to look at different parts of the energy landscape. The picture here specifically is looking at essentially filling the energy wells to force the system out and to find the energy barriers, to see new parts of the system slowly and slowly and slowly. You'll be able to get an idea of what your entire energy landscape looks like. But there's also other methods. So finding the correct collective variable, finding what you want to push, what you want to use as a driver to force your reaction to take place is crucial. And there's loads of resources out there that help indicate how you can do that. CP2K provides a number of collective variables. I've put a link into this. The link is available in the slides. Those of you who are following the slides at home from the GitLab page, you'll notice you can't click the links on GitLab. You also can't click it on while watching on Collaborate. If you download the slides, you should be able to click the links. They should all work, hopefully. But yeah, so CP2K provides a selection of collective variables that you can push, but CP2K also gives you the option of linking with Plumed, which provides even more collective variables that you can use. And so for this exercise, because this entire exercise is a recreation of another tutorial where these things were being done with Gaussian, to try to keep it as similar to the Gaussian session as possible, we are going to be, or to the Gaussian tutorial as possible, we are going to be using the plumed method. Last thing I wanted to talk about is the plumed.dat file. And in the plumed.dat file, you give a certain number of information. The information that you give includes which atoms you're interested in. So atoms 30 and 31 and 29 and 32. Sorry, I've just realized that I'm not sharing my shell just yet, but that's good because I want you to quickly, let's go back 2 things. If you look at this picture and you look at atoms 30, 31, 32, and 29, you'll notice that the bond between 29 and 30 and the bond between 31 and 32, those are the bonds that we're hoping to break to show that we're hoping will break when running our simulation. That's essentially the simulation that we're trying to do. If we're able to break those bonds, then we'll have done a reverse Diels Alder reaction. So with that, let me share my shell again. Boom. There we go. So you'll see VI. It's plumed, isn't it? VI plume.dat. So you'll see the first two things in the plume.dat file is saying, I want a special label for atoms 30 and 31 and 29 and 32. And what you're saying is, I want these atoms on one part. Those are the atoms that will stay, say, on the ring molecule, whereas those are the atoms that will stay on the other molecule. Then you say, essentially here you're defining what sort of thing you're trying to do. You want the distance between those atoms to increase. You set parameters as to how you want this thing to be increased. And then you start to define your metadynamics. So here you're saying that you want to place a Gaussian force field, a fake Gaussian force field every 500 time steps, which has a height of 1.2 kilojoules per mole, to push your reaction out of whatever current energy energy minimum it's in. So that's what this line does. And then the final line is you want to push the D1 distance. So you want to push the distance between the pair of atoms 30, 31 and the pair of atoms 29 and 32. That's what you're trying to push apart. And that's what the final bit of that simulation is trying to get you to do. So at this point, you can, sorry, before submitting, you will need to, did I run this already? Apparently I did run it. So if everything went well, this simulation should not have worked. And I'll tell you why in a sec. Also, I get to show you, see, this is what you get when your simulation does not work in CP2K. You get this lovely abort message telling you why it is aborting. And in this case, it has crashed because it could not find the file system.md.crd. Why it could not find that is because I was silly. Let's remove out and qmmm meta star. Like before, if you look into backup misstep, you'll notice that there's two files there. There's the new system parameters with the tip3p hydrogens, and there's the CRD file, which is the position file from the end of the energy minimization and temperature equilibration that we did before the break, but in a format that CP2K is happy with. So if we copy those across to here, now our simulation can run. While this is running, and I apologize, I should have launched this earlier, but I completely forgot to copy the things across. While this is running, I would like to very quickly, this again runs for about 10 minutes. Two things about this. Firstly, this will run for about 10 minutes. And the second, most importantly, this also will not do anything more exciting than the last simulation, because even with this pushing potentials, or these pushing potentials, we are not simulating this for enough time to have pushed the bonds to break. We are nowhere near enough time to have pushed the bonds to break. If I remember correctly, with this set of parameters, you will need to run for about 24 hours on one Archer node in order to push the simulation. I mean, the reason for this is just like before, we are still simulating this for no more than 1 picosecond. And even with external drivers, nothing really interesting happens in 1 picosecond. And if you start seeing interesting bonds breaking and forming in 1 picosecond of simulation time, I would recommend you really consider whether your simulation is outputting sensible data. So while we're waiting for this, because as I said, this will run for about 10 minutes, and we're only 1 minute in, what I wanted to quickly show is sorry, there we go. What I really wanted to quickly show is the following. don't follow what I'm about to do. This is just to show you a couple of cool things. So one of the files that gets output is this file called qmmm.pause.dcd. And you'll remember, or you may remember, that in the trajectory part of the output, we said we want the trajectory to be output as a DCD format. Well, you can take this DCD format and you can use it to visualize your simulation. And what I'm going to do is I'm going to take 2 minutes to show you how to visualize this within VMD. There we go. So I've copied these DCD files from a longer run that I've run today. You know how I mentioned that I ran one of these for 4 hours earlier today and nothing interesting happened. These are those runs. And I'm going to quickly show you, using VMD, what the system can look like. And I just remembered that actually VMD is that the one? Yes, that's the one. Perfect. So at the moment, this is not particularly exciting. Part of the reason for that is because DCD formats also need the parameters to be input. So what I'm going to do now is I'm going to also load the system.ljmod parmtop. And when I load that, all of a sudden you see that the simulation is fully added. I'm going to bring this back to the very start. And as you can see, I can run my simulation and you can see the various parts of the simulation. I'm running this as 10 times the speed, so that's why it's maybe a bit more jiggly than you'd expect. However, you'll notice if I zoom into the ligand, the bonds that we're particularly interested in are these ones, and they're still very much there. We're about 3/4 of the way through the simulation now, and they don't look like they're moving anytime soon. And that's back to the start. Yeah, so I mentioned VMD as a potential piece of software. Showing the entire simulation is not going to be the easiest way of doing this, but VMD is a potential piece of software that you can use to find information about things. So one of the features it has is you can label certain parts of your visualization software. So you'll notice that I've got crosshairs instead of a mouse now because I've gone on one of the VMD tools to select the select atom thing. And now if I click on this, I get information about this particle, and it tells me it's DAA, it's number 1, and it's nitrogen. So that's what I meant when I said you could use a tool like VMD to open up a PDB file and then click on individual atoms. And part of the information that VMD will tell you is which atom number they are. So that's what I wanted to mention really briefly. Oh, getting a question? Yeah, no worries. I fully suspect that this is still running for another 5 minutes. So very quickly, what I'd like to do is jump the gun a bit and go through the slides real quick. So one thing that we've not touched at, can you visualize orbitals? I do not think that VMD visualizes orbitals, is able to visualize orbitals. I know that there are some software that can visualize orbitals. I think Holly is probably best to answer that question because I can't name any off the top of my head. One of the things that we've not done and we won't be covering in this course, but the material is there for you guys to do it if you want to, and that is look at a Diels Alder simulation in a protein. Part of the reason we've not done this is, well, you've seen how long that simulation takes even for a tiny small system. Can you imagine how much longer it would take if you've got to simulate an entire protein? However, if you're interested in simulating a full protein, you can, we've set up everything for you to simulate the 1C1E protein within the sorry, one second. As part of this course, we have put everything that you need to simulate the 1C1E protein. And the place you can do this is in the session 4 exercises. This is very much the same steps as we've been doing today. But if you guys want to, if you want to go away and try to simulate this, you're more than welcome to. That example should work entirely. If it doesn't, please let us know. We'll do what we can to both help you get it to run and also make sure that it runs for everyone else. So that's the first thing I wanted to mention. The second thing that I wanted to mention is some people who are on courses require or need certificate of attendance to show their universities or show the people they work for that they have indeed attended the courses that they've claimed to have been to. If any of you would like a certificate of attendance, the way to do this is as follows. I've set a mini exercise in these slides. The exercise is entirely written here. If you want a certificate of attendance, please go through this mini exercise and then send the output files specified here to training@archer.ac.uk. It'll eventually get back to me. I'll have a look at them. If the results are what we'd expect the results to be, we will send you out a certificate of attendance. It's just a simple way of checking that you've been to the course and that you've been to, that you've done the course material. I reckon that, with the instructions I've put there, I reckon that if this exercise takes more than 5 minutes, I'd be very surprised. But if it does, please contact us, and again, we'll help you out with any problems you may have. The final point I wanted to raise is, thank you all for attending this course. It's been great having you all here. I'm going to show you the final results, don't worry. I wanted to take a quick moment to mention another few bits of training that are happening that might interest you. The first one I wanted to mention is this course is jointly run by BioExcel and EPCC under the Proeme and ARCHER2 banner. So the first thing I wanted to mention is that BioExcel is a European center of excellence for all biomolecular related simulations, anything that's to do with like simulating of biomolecular systems, be it in quantum mechanically, classical mechanically, how to store your data once it's done, all that sort of thing. BioExcel encompasses all of that. But specifically, what I want to point you to is the fact that BioExcel has a training website, and on that training website, there's a number of webinars that you can join. There's a number of courses, including this one. In particular, I wanted to point out that there is this year going to be an online winter school on biomolecular simulation. You can find the information there at this link. The other thing I wanted to mention is that very soon there's going to be a virtual workshop on best practices for QMMM simulations of biomolecular systems, which seems very relevant if you're interested in this course. For that one, I think that Arno wanted to say a couple of words about this because I think he's one of the people who's helping organize it. Please, Arno, if you want to.
Yeah, okay. Can you hear me all right, Julien?
Yes.
Okay, good. Yes, I wanted to mention this. So, as you know, as everyone knows, this course is kind of a very practical introduction to actually very concretely using CP2K and, as you saw, the preparatory tools to prepare your simulations for CP2K using QMMM. But as some of the questions that have been raised, especially today, highlight, a lot of you are, of course, wondering how you can use QMMM with CP2K or perhaps other software for your own problems. Now, it's important to highlight that QMMM is not just a sort of silver bullet, which you can just will always magically do the job. But there's a lot of things surrounding the usage of QMM, which is complicated and difficult to know whether you're doing the right thing. That goes from how to set up your QM treatment of your region, what kind of density functional to use, what kind of data sets to use. It's a complex topic. So for this reason, BioExcel is organizing a virtual workshop on best practices in usage of QMM for simulation of biomolecular systems. And we will have 6, well, in fact 7 actually, speakers who are experts in using QMM for biomolecular modeling and simulation. The first session of this will happen on Friday the 30th, so that's actually next week Friday. The announcement will be on the BioExcel website and on the BioExcel Twitter account for details about how to join. The page is not yet up, but that will be the webinar that kicks everything off. So this virtual workshop will take the form of a number of webinars between now and middle of January. And at the end of January, there will be a panel discussion between all the experts. And the idea is that this really provides an opportunity for people who are experts in the field to highlight some of the pitfalls and challenges regarding usage of QMM for biomolecular simulation and what you need to look out for. And if you attend these webinars, you'll be able to ask questions. So this covers topics depending on the speaker's expertise relating to enzymology, catalysis, photoreactions, ligand binding, all kinds of different areas. And hopefully they should provide the opportunity for you to ask questions that are relevant to your field. So I encourage you to keep an eye out on Twitter and on the BioExcel website, and please come to these webinars and ask the questions. So hope that will provide useful.
One thing I want to emphasize as well is, correct me if I'm wrong, Arno, but I'm pretty sure that all of these are free.
Oh, yes, absolutely. Yes.
The other one that I wanted to mention very quickly is under the ARCHER2 banner, we also do a large number of, oh, that's the wrong link. We also do a large number of training. The training in for ARCHER2 or related to ARCHER2 is much more HPC focused. So if rather than biomolecular simulations, or if as well as biomolecular simulations, you get your kicks from HPC, I strongly recommend that you look at the link that I've just posted. I will fix these slides so that when you next see them, they will have the correct link. The other thing as well is, while I remember and while I'm on this page, the course webpage for this particular course should either already or will soon have feedback open, and indeed feedback is already there. I mentioned this at the start of the video. If you could provide feedback for this course, if you could take the time to provide feedback for this course, this would be really appreciated. It would, first of all, help us make this course better for next time. As I said, this is the first time we've run it. But also, we consider any feedback that we get for all of the other courses, both the BioExcel courses and the ARCHER2 courses. And the organizers will get this information. So please, please, please do take the time to give us your feedback. We really value it. So with that, I think I've spoken for enough time and that my simulation's probably finished. So very quickly, let's go back to here. I'm not in the right directory. And there you can see simulation's finished and it hasn't crashed this time. Fantastic. Again, this will look very similar to the last one, and indeed, I'm going to do exactly the same treatment as I did last time, maybe with the correct input, to show you that because this hasn't been run for anywhere near enough time, this really is nowhere near This really is nowhere near this is nowhere near the point that we're interested in. Sorry about that momentary lapse. Yeah, as you can see, this result looks almost exactly like the one before, and that kind of makes sense because, as you saw in the parmed file, we're only adding a small Gaussian, a small kick of 1.2 kilokelvin every 500 steps, meaning that by the end of the simulation, at the end, it will have had its fourth small kick. And that's not quite enough to get it to deviate too much from the original results. So not the most exciting thing to end on, but unfortunately, that is what it is. So with that, I think this is where we'll close this course because we're also about 5 minutes over schedule. I wanted to, as a final thing, thank again, like give a huge thank you to Claire Barras for running. I mean, all of these webinars, all of the ARCHER2 webinars are set by Claire in the background. She does a lot of fantastic things. It's really, really hassle-free for all of us organizers to we're just able to come in, present what we want to present and not have to worry about any of the technical sides of things. That's fantastic. I want to give a huge thank you to Salome, who, she made most of the course material. I only changed a couple of bits here or there, but frankly, this was her course. And I also want to give a huge thank you to Salome for taking the time to be here to answer a lot of the technical questions. And finally, I'd like to thank Hert, who gave us permission to use his Gaussian tutorial that I mentioned a bit earlier as a basis for this lecture series. Thanks also to all of you for coming here and listening to us talk about CP2K for way too long. And if there's any questions, we're more than happy to try to answer them. And as Arno says, three last points. The first one is if you've got any questions related to the course lecture or anything like that, please post them on the Ask BioExcel forum. If you've got any questions regarding running on Archer, please send your emails to support@archer.ac.uk. You will all have access to Archer until at least the 5th of November, so please, please, please feel free to run your simulations on Archer while you have the time. Essentially, there's a huge amount of budget. You should be able to do a fair number of simulations, especially CP2K simulations, and hopefully we'll see as many of you as can make it on the 2nd of November, where we will hold a final session, a consultancy session, where we'll try to answer any questions that you found have arisen since this set of material.